Assalamualaikum warahmatullahi wabarakatuh and good day to everyone, especially to our beloved lecturer, Dr. Hamdan. We are from Group 2. This is our assignment for subject ECH 3120, Chemical Engineering Thermodynamics. For this assignment, we are required to discuss and explain about the thermodynamic web. Basically, there are 6 important topics under this chapter that we will discuss further throughout this video. Firstly, the mathematical relation. Next, derived thermodynamic quantities. We also will explain about the fundamental property relation as well as Maxwell relation. And then the dependent of state function on temperature, pressure, and specific volume. And lastly, the thermodynamic web. So as you can see on this screen right now, here are the list of our group members, which are Nur Aisyah, Tain Ifan, Shabil Shahmi, Nur Ayuni Zahira, Wan Zanaria, and also Aina Bushra. So without further ado, let's begin our presentation with me on mathematical relation and derived thermodynamic quantities. For the mathematical relation, basically we are deriving the general formula from the properties, which is the change in any intensive thermodynamic property of interest, Z, can be written in terms of partial derivative of the two independent intensive properties, X and Y. So as you can see here, there are two general formula that you can use, either the first equation or the second equation. Basically, the relationship between these two equations are exactly the same, just differ in terms of the arrangement. Next, I will explain about the derived thermodynamic quantities. Before I go into details about these topics, basically there are 3 categories about the properties. Firstly is measured properties. Second, fundamental properties. And we also have the derived thermodynamic properties. For the measured properties, it is defined by the properties that are directly accessible from the measurement in the laboratory or experimentally derived. So for example, here, the measured properties are the pressure, specific volume, temperature, and also the composition. For the fundamental properties, it is basically the properties that constructed to understand a concept, and it doesn't necessarily exist in the reality. For example, we have the U, internal energy, that come from the conservation of energy, and the S, entropy, that comes from the directionality of nature. Lastly, we have the derived thermodynamic properties. Basically, for the derived thermodynamic properties, it is a combination between the measured properties and also the fundamental properties. So, for example, we have the enthalpy, Helmholtz free energy, and also the Gibbs free energy. So, as you can see here, the equation also will explain you about the derived thermodynamic properties. For example, H, the enthalpy is equal to the U, internal energy, which is the fundamental properties, plus with the pressure times with the specific volume, which is both of that is the measured properties. Also recall that about the heat capacity is also one of the derived thermodynamic quantities. I think that's all from my part. I will pass this presentation toward the next presenter.
Okay, now we move on to the fundamental property relations. The fundamental properties are internal energy and entropy, which derive from the first and second law of thermodynamics. As we can see here from this slide, this is the equation of the first law of thermodynamics. From the equation itself, we substitute the equation into 3 different equations, which are enthalpy, Helmholtz free energy, and Gibbs free energy. And then after we substitute it, we can come up with these new 4 expressions, which are du is equal to T ds minus P dV, dH is equal to T ds plus V dP, dA is equal to negative P dV minus S dt, and the last one is dG is equal to V dP minus S dt. Okay, next, after we figure those 4 equations, we also can come up with definite relations. With this expression or relations, we can write a number of unique relationship by holding a certain values constant. The example here, we have du over ds and du over dv. So by controlling one of the constants, we will be able to get different values. The example here, du over ds, if we control the v, we can get t, and du over dv, if we control the s, we will get negative p. So this is what I mean by controlling one constant, we will be able to get different value. Next, we move on to the Maxwell relations. So Maxwell relations is derived by applying Euler's reciprocity to the derivative of the equation of state. So these are the details of the equation of state. And then Maxwell relations are actually additional thermodynamic property and derivative relationships that can be deduced from the second derivative of fundamental property relationships, which I have explained previously. These relationships can be found by noticing that the order of the partial differentiation of an exact differential has no bearing on the result. It means here that the order of the partial differentiation has no effect on the result. So as we can see here from the slide, these are actually the examples of Maxwell relations, like this one, like these four relations that often used. By using the thermodynamic property relations in conjunction with the Maxwell relations, we can also write heat capacities in terms of T and S, as shown in the slide.
Alright, now moving on to the dependent of state function on temperature, pressure, and volume. Okay, so previously my teammates already shared on the fundamental property relation and also Maxwell relation. So now we are going to find the dependence of Tp and V on any state function. Okay. So the first thing is that we need to start with the fundamental property depending on what the question gives us. So it could be either internal energy, enthalpy, and free energy. And then we can, when we are given one fundamental property relation, it could be either any one of them. So we need to make one variable at constant. It could be either temperature, pressure, or volume. Right. And next, we are going to divide it by dP at constant T, or dV at constant T, or dt at constant V, depending on the terms that we are going to find. And lastly, this is optional, by the way. We can use Maxwell relation to eliminate any terms with entropy change. So it is not necessary. It is not a necessary step, and it is not necessarily entropy. It could be any other terms that we want to omit. It could be temperature, pressure, or volume as well. So below, here is the thermal expansion coefficient and also isothermal compressibility that is being used to eliminate the terms. All right. So moving to the next part. Stop annotation. All right. So we are going to look at the thermodynamic web. All right. So at first, I have no idea what this web is about, but probably I can explain it better now. So the aim of this web is to make us convenient to determine the calculation pathway. All right. So there is a lot of pathway here, right? There is a lot of pathway here. So there is a lot. So so the first strategy in performing the calculation is to take the advantage of the fact that the state properties, which is the term that the value is not going to change, and it is not affected by the path that we took. All right. So the state properties is independent of the past use, right? Okay. So the web is helping us to measure changes in fundamental and derived thermodynamic properties, as mentioned before by my friends. Right. So what is the relation involved in thermodynamic webs? Right. So actually there is a cyclic relation and also Maxwell relation. Cyclic relation and also Maxwell relation. Right. So the Maxwell relation is here at all the reversible arrows, and the cyclic relation is at all the cyclic arrow, All right. So as we can see as well, there is relation without S, relation without B, relations with T and P. So depending on the situation we get, it could be that we are going to find the terms in order that it have no relations without T. So we are going to use this part of the thermodynamic web. So for the cyclic relation, I'm pretty sure Aisha already shared on how does these three terms is related in a cyclic way. So however, I'm just going to add on here. So look at this A, B, and C. All right, this A, B, and C. So the A is the origin. For instance, this one we can also consider this as origin. This one, and also this one. These four terms are the origins, and we can see that there are two outcome from this origin. Right. Color is red. Right. Okay. The terms in red is the outcome from the origin, right? So actually the origin is the product of these two terms. So we can replace the origin with the product of these two terms. Right. And then for that is for cyclic relation, right? So for Maxwell relation, so how does these two is related? So actually, in order to find this, for instance, if we are about to find this term, but actually we only have this term. Okay, so actually, if we already obtain the value of this term, it indicates that we already know the value for these terms as well, because they are the same. They can be replaced. To each other. All right. So just to add on, so for all this derivation in this thermodynamic web, actually there is three different ways that they use to integrate this to generate this thermodynamic web. Okay, so the first one is the pressure explicit equation of state, which is here. Here, and then the second one is the volume explicit equation of state, and lastly is the thermal expansion coefficient and isothermal compressibility. Okay, so here it is, the beta and k value. Beta, this one is beta over k. So here we can see that it is being applied in this thermodynamic web. So that is all from our group, and I hope that this video helps to all of us. Okay, so thank you everyone for watching till the end.